Hello everyone, welcome to the series on field theory. In the last video we saw several examples of field. For example, we saw that the field of rational numbers is a field and the set of real numbers is a field, the set of complex number is a field, the set of integers it is not a field, right? And moreover we saw that if I have a set f is equal to 0, 2, 4, 6 and so on, consisting of all the non-negative even numbers under the standard operations of addition and multiplication, then this does not form a field, right? So now let me take another example. Here I am taking f as the set 0, 2, 4, 6 and 8 with these 5 elements. So it is a finite set, right? And the operations, the binary operations, I am defining them to be addition modulo 10 and multiplication modulo 10. So now what are these and how do we work with them, right? This is called addition modulo 10 and this one is called multiplication modulo 10, right? So now with the simple addition and multiplication we know how the numbers and everything work, but with these we do not see them eventually because we are not working with these often, right? As we do with this addition and multiplication. So now let us see what are these operations, how do they work, and let us see whether these together with these two operations form a field or not, right? So this is the main motive for this video. So let us get started. First of all, I am defining this that if I take two numbers from this set A and B, then A addition modulo 10, B would be what? It would be a number A plus B. It would be not A plus B. It would be here would be the remainder. Remainder of what? If I divide A plus B by 10, it is called mod 10. If I divide A plus B, this quantity, by 10, whatever is the remainder, that comes out to be here. So that remainder is written over here. So A addition modulo 10, B gives the remainder when A plus B is divided by 10, right? Similarly, what does this mean? A multiplication modulo 10, B, this means that I am having the remainder when I divide A dot B with 10, right? For example, if I take these two numbers, 2 and 4, like 2 and 4 belongs to this set, right? So if I take 2 and 4, so I'll have 2 plus addition modulo 4. What would be that? So that would be 2 plus 4. What is that? 6. If I divide 6 by 10, so I'll get the remainder as 6. So 6 is the answer. 6, it would be 6 mod 10. So 6 would be the number that we obtain after applying this operation, right? So you got the idea how this works. So now let us see whether this is a field or not. So for that purpose, what I am doing, I am creating this addition modulo 10 table, addition table, where I am writing the numbers as 0, 2, 4, 6 and 8. I have 5 numbers and I am writing them here as well, 0, 2, 4, 6 and 8, right? So what I am doing, because I need to see if I take 0 addition modulo 10, 0, what would be that? Then I would have to see 2 addition modulo 10 with 2, what is that? And so with for every 5 numbers here, I have to see what addition modulo 10 for the numbers here. Am I clear with that? So let us get started. For those of you who understood what I am talking, they can pause the video and create their own tables. Otherwise you can do with me, right? So 0 plus 0 is 0, and because we are talking about plus, so 0 plus 0 is 0. When you divide that by 10, you'll get the remainder 0. Again, 2 plus 0 is equal to 2. When you divide by 10, you'll get the remainder 2. Then 4 plus 0, that would be 4, divided by 10 would be 4. 6 plus 0 divided by 10, that would be 6. 8 plus 0, that is 8, divided by 10, that would be 8, right? So this would be same ultimately. Now let us see here. 0 plus 2, it is less than 2, so the remainder would be 2. Then 2 plus 2, that is 4, so remainder would again be 4 divided by 10. Again 4 plus 2, that would be 6. Then 6 plus 2, that would be 8. Now here, you see, if you do this 8 addition modulo 10 with 2, you will get 10. When you divide 10 with 10, you will get 0 as the remainder, because 10 is completely divisible by 10. So here I'll have 0, right? So now let us move on to another. In the similar way, you can complete the table. Now for this number, what would be this? If I do 8 plus 4, 8 plus addition modulo 4, what would be that? It would be 12. When you divide this 12 by 10, you will get 2, right? So you can complete the table in similar manner. So you can pause the video and then check afterwards what is it, right? So let me just write the numbers I have computed before. So it would be 8, 0, 2, and it would be 0, 2, 4, then it would be 4 and 6, right? So this is our table for addition modulo 10. Similarly, we can construct another table for multiplication modulo 10. So let us see what is that. So I'm writing numbers over here, which are given in our set, right? So let us do that. So now here, what is the difference? The difference is that instead of adding, you have to multiply. So 0 by 0, so this would be 0, and here it would be 0. 2 multiplied by 0, that would be 0, and when you divide by 10, that again you will get the remainder as 0, right? So here also 0, here also 0, here also 0. The same thing goes for here, because if you multiply 0 with any of these number, you will get 0, and when you divide that by 10, you will get the remainder as 0 only, right? So now next look at this. 2 into 2, that is 4, and when you divide 4 by 10, you will get the remainder as 4. Then 4 into 2, that would be 8, so you will get the remainder as 8 when divided by 10. 6 into 2 would be 12, and when you divide by 12, you will get the remainder as 2, right? Then 8 into 2, that would be 16, when you divide by 10, you will get the remainder as 6. In a similar way, you can complete this, right? So again, I have this 8 over here, and here we have 16, so dividing by 10 gives 6. So you can see that this could be written as 16 could be written as 10 into 1 plus 6. So this is the remainder in our case, right? So in similar way, we have 6 into 4, that is 24. So this would be 10 into 2 plus 4. So here I am having 4. Then 8 into 4, that would be 32. So I'll have 2 over here. In a similar way, you can complete the table. So let me do it for you. It would be 2, 4, 6 and 8. And then it would be 6, 2, 8 and 4. So in the field, we are overall having these numbers only, right? So the operation of addition modulo 10 and multiplication modulo 10 would ultimately results in these numbers only. So now to check for a field, what we need to check for field, we should check the following properties. Firstly, we have to check the properties corresponding to the operation addition modulo 10. What all we need to check? We need to check the closure property, that we need to check whether this is a binary operation or not. Then we need to check the commutative property. Then we need to check the associative property, right? Then we need to check the existence of identity under this operation, and then we need to check that there exists inverse for every element, right? So let us do that for here, and similarly you have to check it these properties for multiplication modulo 10 as well. So we'll check the closure property, we'll check the commutative property, we'll check the associative property, we'll check the identity, and we'll check the inverse, right? And in addition to these properties, we'll also check whether the distributive property holds or not. If all these properties hold, then we can say that this is the field, right? So let us get started. So first of all, we have to check the closure property. So for the closure property, what does it says? It says that when you apply this operation, if you take any a and b belongs to the set F, which is ultimately this 0, 2, 4, 6 and 8. So when you operate this addition modulo 10 onto this, the element should belongs again to the set F. So ultimately the numbers after this, they should either be 0, 2, 4, 6 or 8 only. So from this table you can clearly say that after operating, the elements that appear only are 0, 2, 4, 6 and 8, and no other element is present in this table. So yes, the closure property is satisfied, right? So similar is the case with multiplication modulo 10. So if you can see that every number here is either 0, 2, 4, 6 or 8. So the closure property is valid here also, right? So for next we'll see the commutative property. What is that? The commutative property says that if you do a addition modulo 10b, you'll get same as b addition modulo 10a. These two would be same. So let us check for this for every number. For example, we pick any random pairs, right? We take 4 and 6. So what is the product? What is the outcome? The outcome is 0. So whether you do 4 addition modulo 6 or you do 6 addition modulo 4, right? So it is again 0. So these two are same. So this commutative property holds for these two elements. Similarly, we can take any two numbers, any two different numbers, right? We can take 2 and we can take 8. If we take 2 and 8, the number again is 0. Let me take some other. Let me take 2 and 4, right? So for 2 and 4, what is the thing? What is the number that we obtain? That is 6. Now if we take 4 and 2, then what is the number? The number is this 6. So these two are same. So you may check that this commutative property holds for every element in this set. So this is also true. Similarly, we have to check the commutative property here. So if I take here 4 and I take 8 here, so let us see what we obtain. 4 multiplication modulo 10, 8 would be 2, and then if I reverse it, I take 8 here and I take 4 here. So what I get? I get again 2. So these two are same, right? So we have this commutative property valid here, right? Next we have to see the associative property. That means I have to check a addition modulo 10b plus addition modulo 10c, that would be equal to a addition modulo 10, then b addition modulo 10c. These two should be same. So let us check this for a pair of elements, right? So let me take 4 here, 2 here, 4 here and 6 here. So 2 addition modulo 4, 2 addition modulo 4 would be 6, this 6, right? So let me write 6 over here, and then 6 with 6, 6 addition modulo 6. What would this give me? This gives me 2, right? So the answer would be 2 from the left hand side. From the right hand side, I have 2 here, 4 here and 6 here. So let me look. 4 addition modulo 6. 4 addition modulo 6 would be 0, right? So 2 addition modulo 0. 2 addition modulo 0 is again 2. So these two numbers, they are same, right? So associative property also is valid. So this associative property must be true for every pair of elements in this table. So you need to check it for every pair, but I have shown you that this property holds. Similar is the case with this one. You may check that this associative property also holds, right? Next we have to identify the identity element of this multiplicative group, right? So let us see that. So what we are looking for, eventually for identity, we are looking for that particular element which gives me again A, right? So is there any element that for this particular column I have exactly the same particular column over here? Yes, the same particular column is obtained for the elements 0, right? So if you do A addition modulo 10 with 0, you'll get A again. So I can say that 0 is my additive identity, right? So additive identity also exists for every element in this addition modulo 10. Now let us look at the multiplicative identity modulo 10. What is that? That means what I am saying here is, for this particular column I need to check whether the same column is obtained here for any number. Yes, I can see that here for the number 6. So I can say that if I take any number A, then I do multiplication modulo 10 that number, it should give me A again, right? This is the definition of identity. So in this case the number would be 6. For example, you do 0 multiplication modulo 10 6, it would be 0. Then you do 2 multiplication modulo 10 6, it would be 2. So that means we are getting the same elements. So the identity in this case is the number 6, right? So now so that means the additive identity exists for this. So what is that? It is equal to 6. So let us now look at the inverses. For every element the inverse should exist. This inverse should exist for every element. So now what does that mean? It means that if you take any two elements here, it should give you the identity. And what is the identity in this case? It should give you 0. And for here, what do we have? We have A multiplication modulo 10b. It should give me the identity, that is 6 here. So we are looking for these two things, this thing and this thing. This should be valid for every numbers A and B. Then B is said to be the inverse of A here, and B is said to be inverse of A here. So let me check this over here. So I need to check for every element. For 0, do I have any element for which I get 0? Yes, I get 0 for 0. Then for 2, do I have any element for which I get 0? Yes, I have an element which is 8. So I can say that 2, the inverse of 2 would be 8, right? So next, for 4, do I have any element whose do I have any element such that the 4 addition modulo 10 would be 0? Yes, that is 4 again. And for 8, it is 2. So 2 is the inverse of 8. Then 8 is the inverse of 2, 4 is the inverse of 4, and then I have 0 is the inverse of 0, and for 6 I have, sorry, not 4, 6 is the inverse of 4 and 4 is the inverse of 6. How? Because if you do 6 addition modulo 4, you will get 0, and if you do 4 addition modulo 6, you will get 0, right? So these are the inverses in this case. In this case, let us see what is the inverses for every element. So here we should get 6, right? So we are looking for 6 over here. The inverses here, one thing is to be noted that for inverses, you should exclude 0 from the set. So the inverse should not be obtained for 0 when we are talking about multiplication, right? So here in this case, for 2, what is the inverse? For 2 we have the inverse as 8 because 6 is obtained over here. So that means if I do 2 multiplication modulo 10, 8, it would be 6, right? And again for 8 I have this as 2. So if I do this, I have 6, right? So 2 is the inverse of 8, 8 is the inverse of 2. Then for 4 I have the inverse as 4. So 4 addition modulo 4 would give me 6, and 6 addition modulo 6, multiplication modulo 6 would give me 6. So 4 is the inverse of 4 itself, 6 is the inverse of itself, they are the inverses of each other. So the inverse also exists for each of these. So these properties are satisfied. The distributive property in this case would be, it would be A multiplication modulo 10, B addition modulo 10 C. This should be equal to A multiplication modulo 10 B plus, sorry, addition modulo 10 A multiplication modulo 10 C. They both should be equal. So let us look at these. If I take A to be some number 6 and I take B to be 4, C to be 2, then let me look at the left hand side of this. It would become 6 multiplication modulo 10, then 4 addition modulo 10, 2. So let me first evaluate this. It would give me 4 addition modulo 10, 2. So what would be that? 4 addition modulo 10, 2. It would be 6, right? So it would be 6, and 6 multiplication modulo 6, what is that? It is equal to 6. So now let us look at the right hand side. Right hand side we would have 6 multiplication modulo 10, 4, addition modulo 10, 6 multiplication modulo 10, 2, right? So let us look at these. 6 multiplication modulo 4, this would give me 4, then addition modulo 10, and 6 multiplication modulo 2 would give me 2, then 4 addition modulo 2, this would give me 6. So these two are equal, so our distributive property is also justified, and this should hold for every A, B, C in the set F. You should verify this. So in the last I can say that the set F 0, 2, 4, 6, 8 together with the operations of addition modulo 10 and multiplication modulo 10 forms a field, right? Stay tuned. I'll see you in the next video. Thank you.